Okay, so I'm going to talk first about current density and drift speed. Okay, what does that mean? So remember when I said here that when charges don't accumulate, instead they are removed from the top? The next question should be, well, how fast does that happen? Or how does that happen? And in order to explain that, I have to explain to you what drift speed is. So what happens when electrons move through the lattice? So the motion is through ions, right? So every single time the electron moves a little, it gets hit by the lattice. So think of it as if you were driving on 1115 on the strip here. What's your motion like? You accelerate for a little bit, then the next red light comes, right? Then you accelerate for a little bit, then the next red light comes. Then you accelerate a little bit, then the next red light comes. So they're constantly being stopped by the lattice. So the flow is not smooth, right? And every time your electrons hit the lattice, they lose energy. So they collide and lose energy. So one single electron doesn't actually go far. It's very, very erratic. So the motion of one electron is very erratic. It's constantly accelerate, collide, stop, change direction, then accelerate, collide, stop. So how do we describe that motion? That whole motion is then described by something called drift velocity, defined as VD. And that drift velocity is defined to be in the direction opposite to the external E field. So let's take a cross section of a wire. And let's say I take this length, L, and I am only looking at electrons in here that are moving. So can people tell me the direction of the E field? If electrons are moving that way, will the E field be this way? Which is interesting because we always call the current the opposite to the direction of the electrons. So remember, E and J will have the same direction. Okay. What will the VD direction be? Is that true? Electrons are going that way. So may I write then, if electrons move with drift velocity Vd, the time they take to go distance L is L over Vd. And if the cross-sectional area is A, may I say that in time t, all electrons, all free electrons in volume A times L will move to the right. And if N is the density of those electrons, that is defined as the number of electrons per unit volume, then may I write the net charge passing through the surface as Q equals ENAL. Take a second, make sure that makes sense. If N is the charge of an electron, N is the density, AL is the volume, then is the net charge that's passing through that surface, through this surface, given by that. Also, current density, is it equal to, wait, what was it? I over A? Yeah, was it I over A? Make sure. Yeah, right here. Right? Then is I, may I write I as Q over AT? Is I equals to dQ over dt? That in time t and charge Q, may I rewrite this as ENAL divided by A L over Vd, or drum roll, current density is given by that. And in most cases, we put a minus sign here to remind that current density is opposite to the actual chart direction of the electrons.
My notes bounced off at the end of the semester.
Mm-hmm. Which is clear from this picture right here, right? J goes this way and V goes that way.